Welcome. This is TCPM, TCP maintenance. So if you're not interested in TCP, that might be not the right room for you. My name is Michael Türksen. I'm one of the co-chairs. Yoshi, you want?
Hello.
That's Yoshi, the second co-chair. He's remote. This is the note well, since we are on Wednesday, I guess you have already read it. It's not working group specific. The work in the IETF is bound to it, no matter in which working group you are. This session has been recorded. It will be available on the internet. The slide is wrong. Nick is willing to take notes, so we have a note taker. Yoshi is looking at the chat. If you're on the chat and you want something to be channeled, please put in a prefix to your statement, like MIC or so, and then Yoshi will make sure that we are aware of that. If you are going to submit a draft in the future, which you think is interesting for this working group, please use draft-something-TCPM in the name. Then we are aware of this, and the draft is easily found. That's the agenda for today. It's not completely full. We have 5 minutes left, but we have the discussions which are not that plannable. So we will look at the times allocated to the presentations. We start with working group status. Then we have 2 presentations related to working group documents, and then 3 presentations related to 4 individual submissions. And the final presentation is not about a draft, but about an issue which was in the context of Quick presented earlier this week in the Applied Network Research Workshop. Any wishes to bash the agenda? If that's not the case, then that's what we will work on. This is the list of working group documents as indicated in the data tracker. The first two are green, which means we are done with these documents and they are actually, the first one is actually at the, it's not submitted to the ISG, it's actually at the RFC editor, and I think the second is also there. Generalized ECN, we don't have a presentation on that. That's, I think, most likely the document we will working group last call next. We have Ghost Act, which is a small document about handling acknowledgements for packets you have never sent. That's a short document, should also be last called soon. We have TCP EDO, where we have not a presentation about this time, but a presentation in that area. And the last one is also a working group document, which we have a presentation on. As you see, the dates are not all in the past, but at least some are in the past, so the working group chairs will update the deadlines to make the AD happy. But this working group has a long time history on doing this. Okay, so this means we go, there's the agenda. So we start with Neil. Are you there?
Oh, Martin, you want to say something?
So so do you want to control your slides, Neil, or should I run that?
Let's see. Let me try to request that.
So I pass control to you.
Okay, yeah, I think I'm. All right, can you guys see the slides?
Yes, we can see the slides.
Okay, great. All right, should I go ahead? I'll take that as a yes. Hi, everybody. So I'm Neil Cardwell from Google, and I'm going to be talking about proportional rate reduction. And this is joint work with my colleagues here, Matt and Yucheng and Aditya. So just a quick introduction with some context and background for folks who haven't run into this before. So in RFC 6937, proportional rate reduction for TCP, we published this back in 2013 in the TCPM as an experimental RFC. And at the time, yeah.
I'm not sure we can hear you that well in the room. I don't know whether you can do anything to increase your volume.
Okay. Let me make sure I'm using the right.
Maybe you're not using your microphone from the headphones.
Oh, it's switched.
All right, let's see. Let's see, is that any better?
That sounds better.
Okay.
Amazingly better. Thanks.
Okay, great. Yeah, sorry about that. I did my microphone, and then Meteco changed the source on me. Can everyone still hear me? Yes. Okay, great. All right, so back in 2013, RFC 6937 was published. This was proportional rate reduction for TCP. At the time, this was only implemented by Linux TCP, and it was implemented without rack TLP because rack TLP did not yet exist. And the high-level summary of PRR is that you can think of it as sort of a mini congestion control algorithm that runs only during fast recovery. And at a high level, it sends packets at the ratio of sea wind reduction chosen by the congestion control algorithm. So for example, for Reno, of course, there's a reduction by a factor of half. For cubic, you cut your congestion window to 70% of its previous value. But then also PRR has some logic to handle cases where the volume of in-flight data might actually drop below the target SS thresh. And then PRR in this version had two different approaches for handling this case and deciding how much to send. One called the slow start rate bound, and another was the conservative bound, slow start reduction bound, and then the conservative reduction bound. And then the tricky thing about this version of the RFC was that the implementation was advised to pick one or the other option. And just as a fun and interesting fact, for a flow that mostly operates in fast recovery, its congestion window is mostly controlled by PRR. And this actually can happen quite frequently for flows that are going through a token bucket policer, which is quite common these days, especially in mobile providers. So 6937 BIS, which I'm talking about now, that is an effort that started back in around 2021 after PRR had been around for about a decade. And at this point, when we started the BIS effort, PRR was default enabled in several major TCP implementations. And the working group voted to revise and publish this as a standards track RFC. And then we've since discussed a number of revisions in previous IETF meetings. And I've sort of listed those here. You can go back and take a look at those. But today I'm going to focus on the changes that have been made in the draft since the last meeting. So the current status of the draft, as mentioned a few minutes ago, is that the ISG has approved the draft as a proposed standard, and then the draft has been added to the RFC editor queue. And at this point, the RFC editors are just waiting for the signal to start editing. But we wanted to discuss the draft one more time at this working group meeting in case there were any last-minute suggestions that people had for edits. So there have actually been 8 revisions that we've published since the Rev 13 that we presented in March. And there are links here in the slides if you want to follow those to get a diff. Just a quick warning that it's actually going to give you quite a big diff because there have been a number of changes, 8 revisions, and several of those involved moving sections around. So the diff is quite large, and it might be easier to digest by looking at the diffs for each revision individually. The slides provide links for those, and we'll go through a summary of those diffs. And there were numerous editorial changes to improve clarity, readability, consistency, but there have been no changes to the algorithm. And there are summaries of each revision in the draft itself, but we'll also talk about that now. So in revision 14, this was based on a nice review by Gori Fairhurst. We updated the must, should, may text to be the latest boilerplate and moved it into a separate section. We improved the definition section by making sure that each term actually had an inline definition and not just a mention that this was defined in some other RFC. So each term now has an actual inline definition, the citation of the original RFC that defines that term where appropriate. We added a few missing definitions. We added a paragraph in the relationships to other standards section, which previously just discussed the relationship with congestion control standards. We added a paragraph to discuss the relationship between PRR and loss detection standards and named the loss detection algorithms that are known to be compatible with PRR. And where appropriate, we made the text more generic to other transports rather than focusing just on TCP. Corrected some mentions of MSS versus SMSS. And then we clarified the recommendation to use pacing to avoid bursts and just move that out into a separate paragraph to make that more clear and prominent. In revision 15, we made some small changes. We've fixed the prose description of the initialization of recover FS, added some notes in the example algorithms, and then there were a couple editorial changes based on a review from Russ Housley, and we fixed the abstract and intro to clarify that this document actually obsoletes the experimental PRR RFC. And then we moved the paragraph about measurement studies into a new section by itself to clarify. In revision 18, we just improved the text and description around the figures. Revision 17, we moved the explanation of Ben Jacobson's packet conservation principle to be earlier so that it's actually before the first time we use that phrase. And then there are a bunch of changes based on the nice review from Paul Aitken, ensuring that all the references use proper XREF tags. We moved the definition section to be earlier so that it's before the background section, so that more terms were defined before they're actually used. And then we sort of clarified the motivations for the conservative reduction bound and slow start reduction bound. In draft 18, these are changes in response to Danielle's review. We moved the content in the background section into the introduction section and sort of melded those together and revised the introduction section to make sure that each concept that we're using is first defined before or explained before it's then used, to make it much easier for readers to make their way linearly through the prose. And then we made some simplifications by referring to the reduction bounds just as reduction bounds instead of reduction bound algorithms. Revision 19, there are a bunch of editorial changes, again, based on the Paul Aitken review, second review. The main change here was that we clarified that the pseudocode, which had been using this seal function, we clarified that by sort of explaining that what we mean here is really a sort of division while rounding up. And then we tried to express that in a way that is more unambiguous, but still making sure that this is, exactly corresponding to the implementation in the Linux TCP code. So hopefully that's more clear and more unambiguous. In revision 20, there were a fair number of editorial changes. One significant one was we changed the title of the draft from proportional rate reduction for TCP to the more generic proportional rate reduction, hoping that will make it more obvious that the concepts and algorithm can apply generally to transport protocols and not just TCP. At the advice of Mohammed, we added a new operational considerations section, which has subsections for incremental deployment and fairness and protecting the network against excessive queuing and packet loss. We moved the prose description of the key algorithm elements of delivered data and in-flight and recover FS from the definition section into the algorithm section. Of course, that made the algorithm section considerably longer, so we broke up the algorithm section into subsections to make the organization more clear, where we have subsections for initialization steps, the per act steps, per transmit steps, and then the completion steps. So hopefully that's a more clear and explicit organization. And then we reordered the example and properties sections based on that review. And then finally, in revision 21, that just fixed a typo where there was an accidental extra sentence in there left during the editing process. And that's it for all the revisions. The next step is to hand the pen to the RFC editor. But first, we wanted to check with the working group and the community to see if there are any final suggestions on hopefully just editorial changes. Please make any final suggestions either here during the session or on the TCPM list and CC the draft co-authors. And then, after so if we make changes now in the next few days before we hand it off to the RFC editor, it'll be a little easier because the co-authors, we can just go into the document directly and make the changes. After we hand it off to the editors, it will require more coordination overhead, and the changes, correspondingly should be smaller and purely editorial, and they would have to be implemented by the editors. So definitely we encourage you, this is your last chance to make suggestions for editorial changes. And thank you very much for listening and for everyone's great reviews and suggestions during the process.
Thank you for the presentation.
Yeah.
Are there any comments?
My app is spinning out, so I'm just going to walk to the mic. Hi, Neil. Hope we're paying you by the draft.
Oh, I wish you were.
This is Martin Duke. Just one question. So, obviously, you've made a bunch of changes over the life of this draft. Do those correspond to what the deployed versions have actually done, or are we coming up with new stuff that has not been deployed?
Yeah, so these are purely editorial changes to clarify, and in the one to clarify the existing deployed code, at least I know it corresponds exactly to the Linux TCP implementation. And since there have been no intentional changes to any algorithmic aspects, I presume it also corresponds to the other implementations. There was one clarification where there was a potential for changing the semantics, but that was the change from seal to div roundup. But as I said, I was very careful to make sure that the new version corresponds exactly to what Linux TCP PRR was doing. I presume it corresponds to what the other PRR implementations are doing, but the other authors of the PRR implementations and other OSs are encouraged to double check. I think almost certainly it corresponds to what they were doing, because there's only really an ambiguity if you decided to do this with a floating point implementation. And since thus far, the other implementations we've been talking about are TCP implementations in OS kernels. Probably they were not using floating point, so probably they took the same, had the same interpretation of that seal that Linux TCP did. But I think this is the only area where I can think of where there conceivably might be a change in behavior.
So Gori Fairhurst as responsible AD, thanks for doing all this work. This is good, and I really appreciate the large editorial push here to try and make this clearer. I concur that I don't think anything really changed in all that, except it got easier to read, especially for people outside of TCP. From now on in, we probably need to get approval for any changes. So now is a great time to get back to Neil if you have anything that you see is wrong in this document, and then we will get this published as an RFC. So thanks again, ever so much.
I would like to time-bound the period of comments. So Neil, can you send an email to the mailing list and say, you will forward this to the RFC editor if you don't get any feedback within, let's say, the next 2 weeks?
All right, that sounds great. Will do.
Thank you.
Thank you.
Thanks for the presentation and for the work. Card. Okay. Okay.
Okay, hello everyone. My name is Carlos Gomez. I'm from UPC. I'm going to present the last updates for the draft entitled TCP at rate request option. My co-author is John Crowcroft from the University of Cambridge. So first of all, a quick reminder on the motivation for this draft. Delayed DAX is a widely used mechanism which is intended to reduce protocol overhead. However, it may also contribute to suboptimal performance in a number of scenarios, such as so-called large congestion window scenarios, meaning a congestion window size much greater than the MSS, where saving more than one of every 2 acts may help improve performance, and so-called small congestion window scenarios, meaning those where congestion window size would be up to the order of about 1 MSS, where delayed acts may incur too much delay, may limit congestion window growth, and so on. So this is the main format for the TAR option. The R field indicates the ACK rate, which is requested by the sender, meaning after how many received data segments the receiver is requested to send an ACK. Currently, the maximum value for R would be 127, and there's the special case of R equal to 0, which indicates the request of an immediate ACK while keeping the steady state value of R. On the status of the draft, it was adopted in February 2023. Today I'm presenting the updates in revisions 08 and 09, which aim to address the comments received in the last meeting and also on the mailing list, in this case by Yoshi. Thanks a lot to everyone for the comments received. And let's go through the updates, which are actually in section 3.1, which describes the sender behavior. First, we have added that, of course, over the course of a TCP connection, a congestion window size of the sender may decrease for a number of reasons like congestion control or receiver window size decrease. So if such a change happens and if the new congestion window value is smaller than the number of bytes corresponding to the last R that had been requested, then in order to avoid or minimize potential performance issues, the next segment from the sender should carry a TAR option with an R value corresponding to a number of bytes smaller than or equal to the current congestion window size. And there's other updates on some text that was already in section 3.1. The updates here are highlighted in red. And the context for this is that TAR may produce stretch acts, which may exacerbate the consequences of middle boxes that perform operations like ACK decimation, which might lead to producing, well, loss of ACKs, finally ending up with retransmission triggered by RTO, or now as added in the last update, also by TLP PTO expiration. So we already had some text as reaction in that case with the updated words which are in red. So the reaction would be that if the TCP receiver is known to be TAR capable and the last TAR value requested is greater than 2, the segment carrying retransmitted data should carry a TAR option with R equal to 1. And then once all retransmitted data has been acknowledged, the first segment carrying only new data should carry a TAR option with R equal to 2. So here, what we would do is actually reverting to the default delayed acts operation as a conservative reaction to this event. And as you may have seen, the shoots here are in red. In the previous version, we had a must, and which is the reason for decreasing this requirement level. Well, there was the possible issue that was pointed out by Yoshi, which is that perhaps communication starts over some path where there is no problem with TAR, but then maybe over the course of the connection, there is a route change, and the new route might include or go through a middle box that perhaps doesn't support TAR and maybe discards packets carrying such an option. So in that case, to avoid forcing the packets to always carrying the tar option in the case described here, then we have reduced the mask to a should. So then, depending on the scenario, maybe one might consider whether to proceed like this to actually try to revert to default delete acts or maybe not. Okay, so those would be the updates. And we have also received an IANA early review a few days ago. And basically they request to add the full name of the registry in the IANA consideration section for the experiment ID that is actually already allocated for this experiment. The value is 0x00AEC, which tries to allude to ACK for acknowledgement. And the full name of the registry, which is requested and will be added in the next update of the draft, is TCP UDP experimental option experiment identifiers. So at this moment, we are not aware of any outstanding issues. And similar to what we discussed in the last meeting, perhaps the document might be getting ready to working group last call. So perhaps it would be good if we could get reviews from the working group at this stage, because there had been some reviews some time ago, but perhaps not so much recently, at least full reviews. So yeah, we would like to ask maybe the chairs and the working group, which would be the next steps.
Thank you for the presentation. Are there any questions or comments? So let's make a, oh.
Hey, Neil has a question.
Yeah, go ahead, Yoshi.
No, you have some cues.
So I would like to make a show of hands of how many people have read.
Michael?
Yes?
You have some cues?
You have a cue.
Oh, Neil, sorry.
Yeah, no worries. Can we go back to the slide that talks about the behavior around retransmission timeouts? So it seems like there might be some slightly odd behavior when there's a retransmission timeout, where we have the retransmission timeout, we send one packet with R equals 1, which sounds great, you know, because we want to encourage an immediate ACK rather than a delayed ACK, because we're only sending one packet. And then after that first packet is acknowledged, it's not clear to me what R value the sender would use. It seems like it might go back to its normal approach. And so as it slow start retransmitting a potentially very long range, the CWIN might get to be very large. And then finally, probably the R value is quite large as well, to allow the ACKs to come back efficiently rather than generating potentially thousands of ACKs per round trip time. But then once all of the data is retransmitted, then the sender might go back to sending new data. And then this specifies that then it would have to go back to using R equals 2 when the CWIN might be very large. It might be hundreds of thousands of packets, and thus might force the receiver to send out back hundreds of thousands of ACKs. And so I was wondering about the motivation for going back to like forcing this R equals 2 when we go back to sending new data. Do we need that? Was there a specific motivation for that, or can we potentially remove that rule?
Okay, so I guess we hadn't considered this case, and yeah, we will give it a thought and come back with some proposal.
Sounds good. Thank you.
Cory?
Cory Fairhurst, simply as an individual, but asking about implementations, because if we're publishing an RFC, it'd be good to have some sort of interop. I mean, it's experimental, so what's the situation with implementation?
Yeah, I know that there is prototype implementation actually led by Michael for FreeBSD. At the moment, I'm not aware of other implementation efforts.
Is there any kind of interop to loop through things like Neil said?
Any kind of, sorry?
Interop, as in trying some packet drill type tests to make sure that odd things are captured well.
Yeah, I guess we would need to have like maybe a second implementation to check.
So there are packet drill tests, but I won't count them as interop tests because the person implementing it writes the tests and tests again the same thing. So the answer, I guess we need a second implementation for that.
Well, I wasn't saying needed. I was just interested in implementation experience. So that's helpful. And it'd be good to have more implementation experience. I would love that.
Michael Turkson from the floor, actually wondering if, so you describe here that your extension is triggered from within the TCP stack, like here. Is there also any interest in specifying a potential API? Because I know that in the past we had TCPM extensions like for TCP fast open, where I think every operating system is using a different API, which makes portability difficult. Is there any interest in that? A question to you as a co-author and a question to the working group.
Okay, yeah. We hadn't considered that, but we'll definitely do. And yeah, if there is interest, it may be good to offer something like this. Also to help make it easier maybe to make this available.
Okay. Not at the floor anymore, but acting as like on the floor, I can provide some text for an API.
Okay, that would be very much appreciated.
Okay, thank you. Yoshi was in the queue and went out. Do you want to be in or out?
I'm fine. Yeah, I try to say I don't have a strong motivation to define API because this is experimental RFC. But if once we want to make proposed standard, we might need one. But I don't know if we need for experimental RFC. That's my personal opinion.
Okay, thank you. Then I would say we encourage working group participants to read the document, get some feedback. I get you some text on the API. Okay?
Okay, thank you.
Thank you.
Hello, I'm Ron Bonica from HPE. My co-author Tony Lee also from HPE is right there. And I'd like to talk to you about an experiment I'd like to do concerning TCP extended options. Next slide, please. Oh, I can do it myself. Okay, the motivation for this is fairly obvious. The TCP option field can range between 0 and 40 bytes. For the last decade or so, this working group has attempted to expand that limit of 40 bytes several times for various reasons. This is another attempt to expand it. We'd like to do an experiment, see if it works, and then push forward. Here's the TCP header that we all know and love. It starts with 20 bytes of fixed length fields. It then has TCP options, which vary from 0 to 40 bytes, and then a data segment. You'll find a data offset field in the first 20 bytes. It determines the offset of the data. It also determines the length of the options field, because the option field consumes all the space between the first 20 bytes and the data. It measures in 32-bit units, and its valid values are 5 to 15. Now, why 5? Well, that accounts for the first 20 bytes. 15 says you can have 40 bytes of options, no more. Here's what I'd like to change. In red, you'll see the data offset field. It still determines the data offset, and it determines the length of the options. It still measures in 32-byte units. The one thing that's changed is the valid values. Now the value 0 is also valid. So are the values 5 through 15, which were valid before. And you'll see because of this bit of magic, the maximum option size is greater than 1K. Now, we highly recommend that you do not include a kilobyte of options in any TCP segment. Yes, it is the theoretical maximum, but please don't do that. And here is what the TCP options field will look like. It starts with a length that tells you the actual length of this field in 32-bit words, and the exact same individual options that you always had before. Okay, this is the extent of the experiment. Sounds simple, doesn't it? Well, not quite. This is good enough for an experiment, but there are a few things we need to think about. One is global deployment, the other is backwards compatibility, and these issues are presented in the next slide. Here is a gotcha. Legacy middle boxes and hardware accelerators. They cannot parse segments with the data offset equal to 0. We've tested a few of them, and everything we've tested discards the segment. Sadly, there is no solution to this problem. We've thought about a million other ways to encode longer options. All of them hit the same problem. So there's only one solution to this problem. To not perform this experiment or deploy this feature in the presence of such devices. TCP sessions simply will not come up or will stall. The next is the problem of legacy TCP implementations. And we have two different problems that happen when we're interacting with a legacy TCP implementation, two different backwards compatibility problems. The first is when extended options are used during the three-way handshake. In that case, one of the packets in the three-way handshake is lost. The connection setup times out. The connection never enters the established state. This is annoying, but sadly, no solution is available, or at least no solution that anyone we've talked to so far can think of. So in the case where you need to use extended options during the three-way handshake, you will get a connection timeout when interacting with a legacy TCP implementation. The next is what happens if you didn't use extended options during the three-way handshake? The TCP session comes up, it exchanges packets for a few minutes or a few hours or a few days or a few years, and then finally you use one of these. The legacy box will drop the segment with the TCP extended option. The session will stall. This is even more annoying, but fortunately it's avoidable. In the future, actually the draft already includes this, but not recommended for, not recommended, not necessary for the experiment. In the future, during the three-way handshake, we can exchange a new TCP option. The new TCP option indicates capability to use extended TCP options. If you don't see that during the three-way handshake, don't use extended TCP options during the rest of the TCP session. So, initially we were asking for a call for adoption. A call for adoption would be great, but what we're really looking for is some other players to do the experiment with us. We're doing the experiment in our own code at HP. We would love for some other players to do the experiment either with or without the signaling and test interoperability with us. Once we've done that, maybe we'd come back for another call for adoption. Comments?
Martin Duke, Google. Thanks for this. I don't work on TCP anymore, so I won't participate in your experiment. But I'm interested in the result here. I do think that, to me, the interesting part of this experiment is exactly the middle box problems, because I think your mechanism makes sense and it seems like semantics would work. So I would almost suggest that you reorient the experiment towards that. And I have a few thoughts about that. So there's, I mean, you have it. I think the taxonomy of, handshake and not handshake is important. But the other part of the taxonomy is like critical versus not critical use of extended options. So like SAC is an example of a performance optimization that you can achieve with larger options, right? Mm-hmm. Whereas if you start stacking these various capabilities like fast open and MPTCP and all these other things that have these giant cookies in them, there's like certain connections you could just not negotiate, right, with these extended options. So when you're dealing, and I think those tend to occur in the handshake. So I think it would be interesting to try like some sort of, well, I think part of it is allowing applications to determine if they gotta have it, or if they're willing to function without some of this capability, right? And then maybe some sort of happy eyeballs type situation in the case where it's optional. So what I'm suggesting here is like, so if I need a lot of options in the SYN, but I can live without them, maybe I send 2 SYNs on 2 different ports. And if one of them doesn't get through, then I use the other one. I think these are the kind of mechanisms that I think are probably, just seeing how that works, I think would be a more interesting research problem. I mean, it's not my experiment, so, it's up to you, but I think those would be more interesting research questions to answer than the fact that I feel really confident your mechanism will work in the absence of middle boxes.
Mm-hmm. Okay, so if I understand what you're saying, rather than signaling the way I suggest, what you do is at the beginning, do exactly what Happy Eyeballs does in IPv6. Send 2 SYN packets to different ports. One has extended options, the other doesn't. If the extended options one answers the phone, then you can use extended options. If it doesn't answer the phone, but the one that didn't use extended options answers, then use the other one.
Actually, I think you should use the option as well for that particular use case when you will need bigger options in the middle of a connection. In the specific case where you would like a bigger SYN option field and you can live without a bigger SYN option field, right? That is, I think, the case where you want to do this, right? Because then if you can't live without it, just send the SYN. Mm-hmm. And like if it doesn't get through, then like return an error on the connect call or whatever, because you can't do what you want. You needed this capability, I can't give it to you because it's too many options.
Well, I have a question for you.
Yeah.
Let's say you open only one connection, mm-hmm. and you send the new option to say, I'd like to use SYN options, extended TCP options.
Yes.
The other side answers, you're mm-hmm. good. Then you actually do it. Oh, by the way, there's a middle box in the middle that doesn't understand this option. It just passes it through. Mm. Then an hour later, you try to use the extended options because the TCP peer said it was fine.
Yeah.
You send it, the middle box gets it, and the middle box pukes.
I think, right. So I think that's again, a very interesting research question. If you find that is a problem and your SYN is not big, then yes, you could just you could just use the extended option format anyway, even though you only have like 10 bytes of options or whatever in the SYN. And that would be a way that would sort of be like a proof of life of this capability. Yeah. So I mean, that's a research question. Are these middle boxes going to pass the option and then have a real problem when you actually execute it?
Yeah.
So I think it's a degree of freedom in the experiment.
I agree with what you're saying.
Yeah.
But I think doing the happy eyeballs trick all the time is probably the better solution, because if you just use the signaling mechanism with options, then the middle box won't object until you actually use the extended option. Then the middle box gets nasty. Yeah,
that could be. I mean, I don't have any survey on like middle boxes will pass options and then like that doesn't understand. But
I believe a middle box will pass an option it doesn't understand, but if it can't parse a packet, it throws it on the floor.
Yeah.
There are also other
But let's further the discussion. I'll catch you.
Okay, I'm using too much time, so I'll sit down.
Okay.
Nia?
Yeah, I just wanted to raise the option or a potential approach of saying that this could be a feature that is only deployed in environments where it's known to work. So this would be sort of analogous to the DC-TCP story, where we say, really, you should only use DC-TCP if you're using it within an organization, like in an enterprise, in a data center environment, where you know what the how ECNs can be interpreted by switches along the path and your peer on the other side. So that would be one potential approach if we want to avoid a lot of time dealing with middle box issues. And I just wanted to get your sense of how you would feel about that kind of approach.
Yeah, the routing area is fond of this solution. They like to call it a limited domain. That certainly works and would be happy to go with that solution. But I think the other attempts to use it on the broad internet are interesting too.
Yes.
Yeah, sounds like a fun experiment. So I think it's good to try, but I was curious, you were either careful or it was an accident, I don't know which, but you didn't mention what you don't like about TCP EDO.
The largest problem is applications that need to use TCP extension options in the SYN packet. TCP EDO doesn't even attempt to address that problem.
So the interesting thing is
that's actually our problem.
This would have all the same problems that are described in there, and then when you use it in the non-SYNs, it looks pretty similar in its effect. So I don't know if it actually solves any of the problems with using things in the SYN. It just tries to do it without solving the problems that are listed with doing it.
The problem we have in particular is we want to be able to use extended options in the SYN packet. EDO doesn't even attempt to solve that problem. It just says you can't.
Right, because you can't. Yeah.
That's it.
Okay, I think the queue is empty.
Thank you.
Thank you. So, Yu-chan? Wait a minute, I need to do the things in the right sequence. Now you should. What do I press? I don't know, try it. Let's see.
Okay. Hi, everyone. I'm Yu Chon. I'm presenting a upcoming draft revision for the extended timestamp options. This is work jointly with my colleagues at Google. So what is this extended option about? In a nutshell, it is trying to extend and subsume the current TCP timestamp option RC7323. And we're trying to use a final clock granularity for microsecond timestamp, and also trying to signal more like the delay on the receiver side more explicitly for better RTT measurement. And I'm going to tell you why do we want to do that? Why do we bother to kind of change this very, very old established option? So Google uses Swift, which is a delay-based congestion control for the intra-data center TCP communication, and also other transports. It is part of this BBR Swift. And in order to run Swift very successfully, first we need the RTT measurement to really accurately reflect just the physical network congestion. And we also, for kind of some host congestion, we need different kind of adaptation. And that's why we need this RTT measurement to, in addition, reflect some of this host delays. And we also need microsecond resolution, obviously, because the current millisecond granularity just doesn't work for data center RTT timescale. Let me use a very simple example, which is the TCP pacing. The very standard version uses C1 divided by the smooth RTT. So when you have, say, delay X of even 5 milliseconds, this completely screw up the pacing delay artificially, just because the receiver wants to delay the ACK, hoping to piggyback more data and save some more X. This draft is really needed for us to upstream Swift congestion control to Linux upstream. We don't want to just use our invented option numbers to support that. And why do we even bother to upstream this sort of intra data center congestion control? The reason is for a lot of Google Cloud VMs, they still use Cubic. And we all know Cubic is not going to be the best pick for data center communications. So let me go with some problem we see is existing measurement, which I already talked a little bit. If you use the standard data to ACK RTT today, right, that includes delay ACKs, and we are seeing an increasing NIC receiver side congestion, meaning that sometimes it may take several milliseconds from the NIC to the TCP receiver, which is not really network congestion, right? This NIC sometimes have much bigger buffer than our shallow switches. That requires different adaptation. There is actually some second papers on this already, which we have investigated how, but congestion control is not what I'm going to go detail into in this talk. The third one is even like CPU sleep state. Sometimes if your server process is idle on a particular core, the core goes into deep sleep, and it could take sometimes couple hundred microseconds to wake it up. And this is, again, not really congestion. It's just power saving features. So we really want to kind of filter all that out because they don't really mean network congestion to delay-based congestion control. Another problem is retransmission RTTs. Right now, by the current algorithm, you cannot really measure the RTT for the retransmission. You have to rely on the TCP timestamp option. But again, 1 millisecond granularity or even lower granularity, higher granularity is just not good for data center RTT, which is typically less than or equal 100 microsecond. And then another side effect is that because this timestamp is not that useful, you cannot really use that for the IFAIL algorithm. So IFAIL algorithm is essentially you detect a spurious retransmission and try not to sort of reduce the congestion window based on that. In data center, a lot of time we actually trying to set the timeout a lot faster. It tend to be more aggressive, and we tend to have more spurious timeout. So not having this feature sometimes do have non-trivial effect in terms of congestion control. So what exactly are we proposing? Not really that much different. Still, the TS val and ECR is just being measured in microsecond timestamps. And we would really recommend that some of this timestamp can come and use some of the NIC hardware timestamps, which I'm gonna show later. But additionally, we're including this new field called ACK delay. And this is trying to measure essentially the receiver side of delay, which can happen through intentional delay, like delay acts, or some other congestions, or like the core goes to sleep, whatever. We just want to say exclude it from the network RTT measurement. And we are sort of holding the last 16 bits reserved right now, that we are thinking of potentially adding some of this in-band telemetry later. So let me go through some of these examples, all right? Let's say sender T1 sends a P, P1 as a packet 1, and then you just do the regular timestamp recording, TS recent updates. However, the delay, the X was delayed. And then, the sender follow up by another data packet. And in this case, what you have reflected, the TS-ECR is sort of the original first P1 packet that hasn't been acknowledged. But the ACK delay is accounting to the very last one here that happened on P2. And with that, you can compute the network RTT precisely like it's a 3. And for T7, we highly recommend you use the NIC timestamp, which then will help us like measure the NIC RX congestion for other congestion control adaptation. Okay, and second one, getting more complicated. Let's say there is a retransmission. We send P1, it get lost. We retransmitted the packet, and then which use a newer TS value. Again, we just follow how the timestamp option compute the TS recent and reflected the most recent one because it's a sort of an out of order. Sorry, not out of order, but it's simply an in order packets because the original packet was not received. So that retransmission to the receiver is just a new packets, and which in this case we can still measure some kind of like the ACK delay happens in this case. And again, with that you can compute the right network RTT. So now getting even fancier, what about spurious retransmission? Right, you send the P1 packets, the receiver wants to delay the ACK, but you set a more aggressive timeout, so it time out prematurely and sends the retry the P1. But in fact, this P1 retransmission actually got delayed in the NIC receiving pipeline and took a while to eventually pop to the TCP receiver kernel stack processing. So in this case, from the server or sender's side point of view, the ACK is also delayed, which you can still reflect that back. But here is the tricky part. In this very last ACK, the TS-ECR, the one that you echoed, is the very first original data packets TS val. But the ACK delay that you included is the latest ACK delay. So it gets very tricky because now you have to rely on TCP timestamp option to compute the RTT. But the echo value that you have is the very original packets. And it doesn't make sense to say, oh, the RTT of this is from the time you receive, you send the original packet till the time you receive the kind of like the delay ACK. And in this case, you do have to address this red part, which is the delay between the original and the retransmissions. In our very original proposal, we kind of like include this delta and send it over to the receiver to have it reflected back. And in that ACK delay, which makes this ACK delay feel very weird. Essentially, in the very 00 draft, the ACK delay is 3 plus that red part. We trying to change that, but we haven't find out a better solution. You somehow have to keep an extra sender state to remember this delta, or you piggyback in a different field. We don't have the perfect solution yet, but I just want to give you some of this very complex examples that how RTT measurement can sometimes be very difficult to only identify the truly network delays. And actually that's part of the reason why sometimes the delay-based congestion control have difficulties, because if you work on congestion control, you know priming the congestion signal is the most important step to this essential control loop. Okay, I think I have run out of time, but this is just want to throw a few things that we are still discussing, right? So how to minimize this additional sender states, this weird retransmission delta, and maybe we should include some of the in-band telemetry that was discussed in a different working group. This require Ethernet header changes, but this is about piggyback some of this in-band telemetry data from the receiver back to the sender. And also, how do we leverage the NIC TX timestamps too? There is actually some trade-off. Just imagine that all the timestamp I show you when the sender is sending the packets, if you use the NIC TX timestamp instead of the TCP times sender timestamp, then the advantage you get is an even more pure physical network delay. But the disadvantage is that now you ignore sometimes between TCP layer sending the packet till the NIC actually sends the packet into the network. There is some kind of like a QDIS congestion in Linux, right? There is sometimes some congestion that you may want to handle that and address that. And then the last one is, right, like, even for ACK delay, there is so many different delay. There is intentional delay, there is the congestion delay, there is the power state delay. There is maybe sometimes if you use this guest VM, there is some network virtualization driver delay. Do you want to disambiguate all that so the congestion control can take advantage? That's also worth a lot of consideration. So that will be all, and happy to take questions.
I think we ran out of time for taking questions. So,
okay, sorry.
Thanks for the presentation, and also looking forward to an active internet draft to be submitted soon.
Sure, yeah.
Thank you. Now it should work.
So hello, I'm Mathieu Bart. So I'm introducing bug in the Linux kernel because I'm maintaining MPTCP, and I'm going to talk, of course, about MPTCP and two extensions. So this work was done with Olivier, who is in the room as well. So a quick recap about MPTCP, just in case. So it's an extension to TCP, of course. It's using TCP option space, and it allowed to exchange data for a single connection over different paths simultaneously. So it brings new capabilities. Here we are going to suggest two unrelated and independent extensions. So one that we call DSX extension and the other one external keys. Both of them are negotiated at the connection time. And in the design, we really want to have a possibility to fall back to normal MPTCP. So the first one, DSS extension, the goal is to accept packets of more than 64K with MPTCP. So first, why is it an issue? Why we have this limitation is because in MPTCP, when we carry data, we need to specify the data level length, and it is limited to 2 octets, so 64K. The reason why we want to have that is that at least in Linux, it is possible to build egress packet of more than 64K, at least since 2022. For the motivation, so either it's because we can have packets of more than 64K on the wire, like with IPv6 and the jumper frames, or because GSO is used, so it's more for internal packets. And in the Linux kernel, we have this very simple code where if the GSO max size is more than 64K, then we limit it. And we introduced that because we had an issue and we had to fix that. So we were thinking, oh, it's a bit a shame of having this limitation. It affects a bit the performances. And maybe there is a solution. The solution would be to extend the data level length to 4 octet. And by doing that, we would like to drop the checksum. So the checksum is the MPTCP checksum, not the TCP one, of course. And this one is rarely used. It was used to detect some middle boxes, but in production we see that it's not really used. We saw that because there was an issue, a bug, and nobody complained about that for a while. And the idea would be to have a negotiation. So when we initiate the MPTCP connection, we would like to use a reserve flag in the SYN, if it is okay, because it looks like the flags from D to G are not used. And to be able to have a fallback to a normal MPTCP, here we would keep the data level length of 16 bits in the MP capable, so at the initialization of the connection, just in case the server doesn't support it. And that's all I wanted to say for this extension. Do you have already some questions? Yes?
Gori?
Gori, as an individual, you're expecting to send packets on the wire which are bigger than 64 kilobytes? Is that what I heard?
So, or at least my main reason why I would like to extend this field is more for internal packet for GSO. But if people want to use IPv6 and jumper frames, maybe they also want to use a packet on the wire which are more than 64K.
I think there are two different things. If you're going, I was going to ask how you were going to do integrity checks for 64 kilobyte packets or bigger, and ask how you considered this.
Sorry, I didn't.
This is the classic jumbo frame thing that keeps coming up, is people say there's jumbo frame support, but when we actually look at the code, we don't think it's that well exercised, and I'm worried about the integrity check option that might happen here. The checksums are not designed for 64 kilobyte packets. How would you extend them to cover the whole amount of data you're sending?
No, that's a good point, yeah.
Okay.
I didn't really think about that. My main point was for GSO, but yes.
Okay, well, you opened the can of worms and asked about large packets, so I thought I would ask. Thank you.
Thank you. So if there are no other questions, I will talk about the second extension. So again, it's not linked to the previous one. The motivation of having external keys, because with the MPTCP v1, the keys are sent in clear. So attackers seeing initial handshakes can hijack MPTCP session. That's not really critical because it's a bit similar to TCP, where such attacker could intercept and inject data. The keys, they are not used for to encrypt the whole connection. They are used to be able to establish new subflow, to announce addresses and reset. This is linked to a previous draft from Christophe Page, but I'm going to explain what it is. So application level protocol already negotiate keys, like with TLS, SSH, and the idea would be to use these keys to secure MPTCP. So in terms of implementation, at least for Linux, the application will only have to share the keys with the kernel. A bit similar to the previous extension, the negotiation would be done in the initial SYN, and we would like to reserve another flag, E, for external keys. And the fallback would also be okay, because the client send a token in the third ACK. So in the RFC, we can see this being presented. It might be a bit confusing because it's important to know that the MP capable in the SYN, you don't have the option send a key and the receiver key. You only find the first one in the SYN ACK and the rest in the third ACK. So we have a way to do a fallback, and here we only have to share tokens that would be picked, not derived from a key. So it would be also easier for the implementation. Now there is a need to be able to tell the other hand, at least from the MP-TCP level, that a new key is being used or going to be used. So we would have a new signaling option, similar to other ones that we have with MP-TCP, with that address and others. But here, in this new signaling option, we would have a flag that we call K, which would contain the key ID. And it's only 1 bit, it's fine, because we think that we only need 2 keys, the current one and the future or previous one. So only needed to have 2 when we want to switch to a new key. This signaling option can be sent in an ACK, so it might be needed to have a way to retransmit it. Of course, for all the options that use the key, we will also need to have a way to inform which key is being used. That's why we would like to use one of the reserve bit to use the key ID. Only 1 bit is needed. And we will need to do that in the MP join, the address, and the fast close. For the fast close, we would also like to no longer include the receiver key because it's coming from the user space. Maybe it will be reused later for other reasons, but instead we would like to use the truncated HMAC. And that's it for the second extension. Do you have any question or ideas? Oh, I also forgot to say that thank you, Yoshi, for the first review.
Yoshi.
I have just one clarification question. So, in order to use this option, so both endpoints need to share the key beforehand, before initiate MP-TCP session. Am I correct?
Sorry, I missed the end of the question again.
Oh, okay, sorry. So, before initiate MP-TCP session, you need to have a shared key for both end side. Am I correct? Then if this is correct, then in order to use this option, beforehand you have to establish TLS session or SSL session beforehand. And then after that, you need to initiate MP-TCP session. Am I correct?
Yeah, so the key would only be used when you need to establish a new subflow, or at least probably the first step that you will use it, or to announce something else. So we think that it would be fine to have the keys being exchanged in the first subflow at the beginning of the connection. It could also come from an external channel, maybe, if there is a need to directly be able to send MP join or add address. I hope
Okay,
it answers the question.
Yeah, thanks.
Thank you.
Any other questions regarding this? Two MP-TCP related documents? If that's not the case, then thank you. And I need to do some clicking.
So sorry, it's me again. This time not about MPTCP, so it might be more interesting. It's about opportunistic hack in TCP. It's work that I'm doing with Olivier and Louis, also both in the room. And quickly, what it is, probably a reminder, because it's a misbehaving receiver, that we call attacker on the slide, could send ACK for not yet received data. So all of this would push the sender to send at a higher throughput than expected. So that's what you can see on the schema over there. The attacker would receive only one segment and say that, oh, I received up to another segment I didn't receive, but the server already sent it, so it will think that, oh, okay, that's fine. I can send more segment to you at a higher rate. So this is not a new problem. It has been already documented in 1999. So Neil was working on that. Maybe I should not say that it's an old document, because Neil is there. Neil is young, so it's all good. He's at least 26 years. But anyway, why are we looking at opportunistic hack now? So there was a similar issue in Quick that has been presented by Louis yesterday. But Quick has a solution for that, because the sender can skip packet number. It's not a continuous, it's not about bytes like in TCP, it's about packet number. They all have an ID. So today, most Quick server implementations support the solution. But what about TCP stacks? So we look at the Linux TCP stack, and we saw that it's still possible to have opportunistic attack. So there was a very small proven concept where you can see that the client is limited to 10 meg, and the server would be happy to send 300 meg and thinking that everything is okay. Also with this kind of attack, if the attacker is cautious, it can be quite undetectable. Why? Because on the server point of view, it will simply see that it receives acts that looks okay at a higher rate, and that's it. So detecting such attack can be a bit difficult. So the most obvious thing that you can monitor is the unseen ACK, so receive an ACK for unseen data, sorry. In Linux, there is a trace point for that, but it's not that easy to get the number, so maybe it's not something that is being monitored. But apart from that, it might be difficult to detect that an attack is in place. Maybe we can get some hint if we want to check out the data, like limiting the active flows with large congestion windows, and of course, going in one direction. We can look at the retransmission, because maybe if there is no retransmission, it's a sign that there is an attack, but just a sign. Also good to look at the ratio between the ACK that are received by the server and what is being sent. Also looking at the RTT variation. But most of them can be kind of faked by the attacker, or it might depend on how the attack is being done. So for the mitigation, when we think about that, we have some constraint because we don't want to change the TCP protocol. We don't really want new TCP option or behavioral changes, so we cannot do exactly like what Quick is doing. We don't want to just refuse ACK for 2 large segments, because that's not allowed by the protocol. We don't want to impact performances, of course. So we cannot simply stop and wait for feedback. And we don't really want to rely on other layers like TLS heartbeats. So when we were looking at the countermeasures, because we don't want to break the internet, we could randomly drop a segment in long downloads. So on the schema, you can see that the server is dropping the segment number 4 on purpose, And if the attacker said that it received the number 4, then we can say that, oh, we detected an attack and we can stop the connection. So if the server receives dupax or SACs linked to this segment, then it's okay, we retransmit. But we have header flag blocking. There is a cost in terms of performances, latency, buffering, and everything. So probably we can do some optimization there. A first one, a bit obvious, is that we could tell the TCP congestion control on the server side that it's not a proper retransmission. Another optimization would be that we could delay the retransmission by more than half an RTT. So we don't have to wait for dupax or SACs being retransmitted, but it might be then more complex to detect that there was really an attack. And we could also add some condition before doing that kind of stuff. We could limit to flows that have a large congestion window, also that are active in one direction. We could check the retransmission, the ratio that I mentioned before, the RTT variance, even if everything can be fixed and depends on the attack, but that might help not to introduce other issue in other performances issue. We could also exclude some prefixes. We could have a way to disable it because, of course, in some condition, you know that you will not have an attacker, and maybe we can have more conditions. Also, there might be also simple alternative that already exist. So at least on Linux, we can easily limit the throughput per connection. So the application can use the socket option max spacing rate to do something like that. Or we could also modify maybe the kernel to slow down the connection in some condition, like maybe when just receiving 2 large segments that are being hacked. Or maybe we don't need to do anything because, as I mentioned, it's not a new concept and we don't think there are really solutions today, but also we wonder why. Maybe it's not causing bad troubles, or maybe we think that it's not exploited so far. We read that in the past we were mostly saying that, oh yeah, but you need a TCP user stack for that, so it might be complex to put that in place. Maybe it's also easier today to have large botnet than smaller ones doing opportunistic acts. Maybe the simple countermeasures that I presented are enough, but maybe not for everybody, especially the smaller actors, or maybe the ones who cannot really have pacing because they don't know exactly how the client is using the, depending on the use case. Or maybe, in fact, we don't know if anybody is really actively monitoring that, because maybe most of the monitoring is done on the ingress, but maybe not checking the correlation with what's happening on the ingress and seeing a large uplink being used. So the question was more, what should be done?
Any comments, ideas, suggestions? Neil.
Yeah, I think it would be interesting if you want to continue this work, if you can work on mitigation strategies that don't have a significant performance overhead. Just kind of thinking out loud or sort of trying to summarize one potential thought I've had over the years. So in our original paper, one of the ideas we suggested for mitigating this was to have an explicit nonce that the sender would send, and then the receiver would have to echo, and you could sort of tell if the receiver, probabilistically with high confidence, tell that the receiver was was sending bogus acts if it was using the wrong nonce. But you might be able to do that implicitly by doing something like varying the packetization boundaries and checking to see if the receiver is acking packets with boundaries that you never actually used. But of course, that's an interesting research question because there might be legitimate buffering or emitter blocks implementations that cause you to acknowledge packets of boundaries that you didn't actually send. But I think there might be something like that might work, and it would be great to see experiments done in that space.
Yeah, thank you.
Yuchon Chen, I personally think we don't really need to solve this, but if we really want to, because I wouldn't call it a tag, right? You can just trying to opportunistically acting, hoping to receive data faster, but you are also risking that screwing up, meaning like you are acting future things that the sender never sent. And the sender can just have this built-in logic to detect that, oh, you are not your acts are not making sense too many times. So maybe log an alert and that. And I think that's good enough. Because I think there is a limit that you can really act into the future, right? So that's my opinion.
Yeah. And also in the proof of concept that we built for that, we also saw that so because there are too many packets that are lost on the way from the client, from the server to the client side, the client doesn't know exactly what's going on, exactly where the server was. So it always tried to predict where it should be. So when it goes over and when the server starts to see act for unsent data, then the client is completely lost and doesn't really know, oh, in fact, I'm not receiving anything. So I need to restart from one, but I don't know exactly which one because I lost too many. So we think that the attack can work, but you cannot have a perfect attack with that, except if you are cautious and you say, okay, I only try to double the amount of data that the server sent to me.
Yeah, so I think it's very easy to shoot yourself in the foot. And so I feel the attack degree is kind of limited. Yeah.
Maybe.
Michael Tuxen from the floor. I think this is so the attack has been known for a large amount of time. So I think this is an indication that whatever mitigation you use, it must be simple to implement. A complex mitigation seems to be more like a problem of introducing potentially bugs.
Good point. Thank you.
Louis Navarre from UC Louvain. So just to jump to the previous question, during this work with Quick, in Quick, normally when you see an ACK with ranges of packets that were never sent, you directly close the connection because it's an error receiving ACK for unsent packets. And so we just saw that by being a bit cautious and avoiding to sending, we can perform the attack without jumping over this sequence of packets and jumping and sending too many acknowledgements compared to what the server sends. So what I mean is that we can do the attack cautiously and still perform the attack. So we show that in the paper. So I think just counting the number of times the client was too early in the acknowledgement he sent is not sufficient. That's only my opinion from what I saw in the paper. But just counting the number of times we were out of this window and with the trace, the probe you have, for me, I think it's not sufficient.
Thank you.
So thank you very much for the presentation. We ran out of time. I think this closes the TCPM session for this IETF. Looking forward to see you all in Montreal.